Okay, question 45, post-order traversal of a binary tree. Iterative implement an iterative post-order traversal of a given binary tree. Return the list of the keys of each node in the tree as it is post-order traversed. So now looking into the function signature, the function name is post-order, and the input data is a tree node for the root, and the output data is an integer list. And possible corner case is when the root is null, then we can just return the empty list. And the solution here is to basically visit all the nodes, and during the visit we need to create a stack to store all our visited nodes. And then also to visit we need to set out a while loop and also two pointers, pre and cur. And based on the relationship between the pre and cur, we can know whether it's a good time to add an element to the list and also pop it out from the stack. So there are three situations. So when you're going down, going up from the left, or going up from the right. So in the beginning, your pointer basically, you have the cur on the top, pre on the top, and then you continue to move down. And then at that time, your pre still on the top, and then your current is still on the bottom. And so when you are going down, you basically need to check whether a node has a kit or not. If yes, then we need to add the kit into the stack. If no kit, then you can add yourself to the list and then pop. And the second situation is if you going down, and then you start to go up. And then if you go up from the left, then you need to check whether you have a right child or not. If no right child, then you can print yourself. You can add yourself and pop yourself. If you have a right kit, then you need to add a right kit to the stack. And then continue to move the pointer. And then another situation is you going up from the right. That means, okay, you already visit all your kits, then visit all your kit and add all your kits into the list. So now you can add it yourself and then pop yourself. Okay, so that's the big idea. Overall time complexity is O(n) because we need to visit all the nodes, and the space complexity is O high because basically when we visit down, from the top, from all the way, you basically need to store all the loops on the way to the stack. So that's the time you use the space the most, is to have all the loops on the stack. So it's all high. Okay, now looking into the code. So the first is to create a new list, and then if the root is null, then you can just return an empty list. And then we create a stack to help us to store visited nodes. And then in the beginning we set up the pointer pre. First it's a node, and then we start to add a root to the stack. And then we have this while loop. When the stack is not empty, then we need to continue all these process. So when we go into the loop, basically there are three situations, whether you're going down or going up from the left or going up from the right. So if you're going down, then you need to check whether this current node has a kit or not. If it has a kit, then you need to add a kit to the stack. If you don't have left kit, no right kit, then you can add it yourself to the list and then pop yourself out of the stack. And then the second situation is when you're going out from the left, then you visited the left child, but then you also need to check your right kit. Then so you check whether you have a right kit or not. If you don't have a right kit, then you can add it yourself and pop yourself out. Otherwise, you need to add your right kit into the stack. Okay. And a third situation is when you're going up from the right. Then you already visited right, and then you added a right kit. So now it's your time to add yourself to the list and then to pop yourself out of this stack. So, and then when the iteration finishes, right before it ends, we need to move the pointer pre and cur. So this step is important because this the movement of the pointer help us to know, in any given point, what's the relationship between the pre and the cur, and then we know, whether it's going down, going up from left, or going up from right. So at the end, when the stack is empty, then that means we already visit all the nodes and added all the nodes into the list, and then we just return the list.